In this lesson, we will study geometric sequences and series. A geometric sequence, or geometric progression, is a sequence an with a constant common ratio r, which is defined as ratio between any term over the previous term, so an plus 1 over an. And that must be true for any natural number n. Here we have some examples of geometric sequence. The first one is 5, 10, 20, 40, and we could generalize this pattern as 5 times some power of 2. For example, if n is 2, then we have 5 times 2 to the 1, so it's just 5 times 2, which is 10. If n is 3, then we have 5 times 2 to the 2, which is 5 times 4, so it's 20, and so on. So this general term really works for the sequence. Okay, so what's the common ratio for this sequence? If we take any two consecutive terms and divide the last one by the previous one, 10 divided by 5 is 2. 40 divided by 20 is 2. So common ratio for this sequence will be 2. And another example, here we have 8, 4, 2, 1, 1/2. It's easy to notice that we are taking half of the term to produce the next term. Therefore, overall, the general term of this sequence would be 8 times 1/2 to certain exponent. And again, we can check if n is 2, then 1/2 to the 2 minus 1 is 1, so it's just 1/2 of 8, which is indeed 4. So that works. What is the common ratio here? Well, as we noticed already, it's 1/2. Okay, so looking at these two examples, we can notice something common to both of them. For example, the general term consists of the first term. In both cases, first term is here. This is 5, this is 8. And then it's the common ratio, which in this case it's 2, to some exponent. And over there, the common ratio is 1/2 to the same exponent. Okay, that may not be a coincidence. That may lead us to a formula for a general term of a geometric sequence that will depend only on the first term and the common ratio. So let's observe the geometric sequence. Since we know that the ratio between any consecutive terms is r, then if we start with the first term a1, then the next term will be a1 times the common ratio r. And the following one will be the previous one times the common ratio r. So that becomes a1 times r squared for the third term. And the fourth term will be the previous term times r. So it's a1 times r3. Notice that this exponent 3 is 1 lower than the index of the term. So generally, if we are talking about nth term, it must follow the pattern the first term times r to the, and the exponent is 1 lower than the index n, so it's n minus 1. And that's how we come up with the formula for a general term of a geometric sequence. Okay, let's see how the geometric sequence behave. If we start with -3 and we go with the common ratio -2/3, what are the first 4 terms of such a sequence? Well, the first term is -3 for sure, because that's what we start with. The next one will be the first times the common ratio r. So negative and negative makes it positive. So we can observe that since the common ratio is negative, the sign will alter. So every next term will have the opposite sign to the previous one. So this time is positive, and then 3 times 2/3 is just 2. Now 2 times -2/3, the sign will change to negative, and 2 times 2 is 4/3. And the next one, again, we change the sign, it will be positive, and 4/3 times 2/3 is 8/9. And so on, but we need just the first 4 terms. Okay, now we want to develop a general term for the sequence, and then find out the 10th term of it. So general term an is equal to according to our rule, we should start with the first term, negative 3, and multiply it by negative 2/3, which is our common ratio, to the n minus 1. Now we could treat the sign separately, because this negative in a bracket can be seen as negative 1 to the n minus 1, and we also need to multiply by another negative in front. So altogether we could write this sign as negative 1 to the n rather than n minus 1, and then don't use negatives anymore. So this term could be seen as negative 1 to the n times 3 and times 2/3 to the n minus 1. So we can use this formula and figure out what 8/10 is. Negative 1 to the 10 will be positive, so the overall answer will be positive. We don't have to worry about sign anymore. And now 10 minus 1, that's 9, so the numerator is 2 to the 9. And this 3 can be cancelled with 3 to the 9, so in the bottom we can write 3 to the 8. You may want to check on this by yourself. If we need to raise some numbers to very high exponents, most often we don't really need to perform those powers. Just leave it as it is. This is a perfectly good answer. In the next example, we want to find the general term of the following sequences. In order to do that, we need A1 and R. Well, A1 is shown, we know it. What's R? R is the ratio of one term divided by the previous term. So 0.3 divided by 3 is really 0.1. So the common ratio that we're going to use is 0.1, and then we can use the formula for the general term of geometric sequence. So AN equals A1, which is 3, times common ratio, which is 0.1, to the exponent n minus 1. And in the second example, again, A1 is given, negative 5a. What's the common ratio R? Well, we need to divide 5a cubed over the previous term, negative 5a. So we have a negative sign, the 5 cancels, and we've got a square. So negative a square is a common ratio. Therefore, an equals the first term, negative 5a, times the common ratio, negative a square, to the n minus 1. So how can we simplify this? First of all, let's separate the negative signs. Negative to n minus 1 times negative is negative 1 to n. Then we have 5, and then we have a to the 2 times n minus 1. So we'll have 2n minus 2, but then in the second we need to add this 1. So altogether is 2n minus 2 plus 1, so it's minus 1. And that will be our answer for the general term. Next, we want to find the 9th term of a geometric sequence, whose second term is given, and it's 3, and 5th term is given, and it's 24. Similarly as with arithmetic sequence, in such questions, we have two variables to look for, the first term and the common difference. So we set up two equations, first equation using this information, second one using that one. So second term is 3. Second term is the same as A1 times R, and that's 3. We don't know neither A1 nor R, but that's okay. We'll create another equation, and the second equation compares A5. A5 is the same as A1 times R to the 5 minus 1, which is 4. On the other hand, it is given to be 24. So we created a system of equations, this one and that one, and we need to solve them for A1 and R. Therefore, the strategy for solving such equation is by dividing them side by side. So if I divide the second equation by the first equation side by side, I end up with A1r to the 4 divided by A1r on one side, and then 24 over 3 on the other side. Here we can reduce a1, and that was the goal, because the remaining equation will involve only one variable, so we'll be able to solve. So r to the 4 over r is r cubed, and 24 divided by 3 is 8. So r must be 2. Okay, as soon as we have r, we go back to one of the equations, for example the first one, and just plug it in r equals 2. That gives us the solution for a1. It is 3/2. Okay, so now we have both variables. Therefore, we can answer the question. The question calls for a9. What's a9? a9 is a1, which is 3/2, times r, which is 2, to the exponent 9 minus 1, which is 8. Therefore, altogether we have 3 times 2 to the 8 divided by 2 is 2 to the 7. So that's the 9th term. Again, there's no need to evaluate this. This is a pretty large number. We can stay with the product of powers of prime numbers. That's perfectly fine. Now we're going to develop the formula for the partial sum, Sn, of the first n terms of a geometric sequence. Let's write the Sn. So it's a sum of first n terms, a1 plus a1r until a1r to the n minus 1. And then we're making a trick like that. We're subtracting the same sum but multiplied by r in order to move each term one column forward. So if I multiply this Sn by r, then this term becomes a1r, which is here, that one a1r squared, which is here, and so on until the last term, when multiplied by r, goes over there, a1r to the n. And we're subtracting all of them. This is for the sake of reducing the same terms. And that's beautiful because nearly all of these terms are reduced, except for the very outside ones. So what we end up with is Sn minus Rsn equals a1 minus a1r to the n. And now if we factor common factor from each side, that means Sn from here, it will leave us with 1 minus r, and a1 from there, and it will leave us with 1 minus r to the n this time. Then it's easy to solve for Sn. It's enough to divide by this bracket. So we have a1, 1 minus r to the n, everything over 1 minus r. And that's a formula for the nth partial sum. Let's highlight it. That will be important to know. So let's recall this formula from the previous slide. It was the nth partial sum of a geometric sequence is a1 times 1 minus r to the n over 1 minus r. Obviously, we can divide only if r is different than 1. But again, if r is 1, then we deal with a constant sequence, which would be very easy to calculate. The nth partial sum is simply n times a1. So we don't have to worry about r equals 1 at all. Let's analyze this formula. If absolute value of r is smaller than 1, that means the common ratio by itself, regardless of sign, has a form of proper fraction, then if we raise a proper fraction to a very high exponent, this fraction becomes very, very small. So if n goes towards infinity, this term r to the n will actually try to reach 0. So this can be neglected. It will be so small that it's not really relevant. Therefore, the general term of a geometric sequence a1 times r to a certain high exponent will actually approach 0. This will go towards 0 as long as the exponent is very high, as long as n approaches infinity. And also, we can talk about infinite sum. The infinite sum will exist because, imagine this part is going towards 0. So 1 minus very, very tiny thing is nearly 1. So overall, if n goes towards infinity, we can talk about the infinite sum of a geometric series, which is actually just the first term divided by 1 minus r, because we can assume that this bracket in the numerator is 1. So the formula for the infinite sum seems to be even easier than the formula for the partial sum. But that happens only when absolute value of r is smaller than 1. If absolute value of r is actually bigger or equal 1, that means could be some improper fraction, then the infinite sum does not exist. Okay, now we need to practice calculating various sums using these two formulas, either the partial sum or infinite sum. Well, let's see the first example. This is a sum of 15 terms. So this is the same as S15. And what's our A1? The first term. Well, the first term is when n is 1. So this is 0. And 3/4 to 0 is 1. So the first term is really just 2. And what's the common ratio? Notice that the common ratio is actually this number under the exponent. So it's 3/4. Because the next term will be multiplied by 3/4. So 3/4 is the common ratio. Okay, so we can use this formula for S15. We have the first term 2 times 1 minus 3/4 as common ratio to the 15, and then over 1 minus 3/4. Since 3/4 to 15 is pretty small number, it's not easy to calculate by hand, so let's use our calculators and figure out the overall value of this. When you enter this expression to the calculator, make sure that you use a bracket around the whole denominator and also these two brackets over there. Instead of 3/4, you could use 0.75, or if you use the division button, for example, here, then use another bracket, just in case. So please evaluate this by yourself. This is supposed to end up to be approximately 7.893, up to 3 places. Okay, let's try the next example. Here we have infinite sum. So in order to know if the infinite sum exists or not, we need to check what's our r. Well, r is -1/5, which means it's a proper fraction. The absolute value of r is smaller than 1. So we can find the value of the series by calculating infinite sum, which goes according to this formula, A1, which is, if n is 1, this is 0, so A1 is actually just 1. So A1 is 1 over 1 minus common ratio, but common ratio is -1/5. So we have double negative here. And if we multiply the top and the bottom by 5, then we end up with 5 over, and here's 5 plus 1. So this whole sum is really equal to 5/6, less than 1. But it's positive, even though we had so many negative terms inside. Every second term is negative, every second is positive. Okay, let's look at this interesting case. This is 0.4 repeated. We know how to convert this repeated decimal into a common fraction without using series. But let's look at the series approach to justify that 0.4 repeated, as we most likely remember, is the same as 4/9. Let's see if this geometric series theory will help us to justify this fact. First of all, notice that 0.4 repeated, which is like 0.4, 4, 4, and 4 forever, can be written as 0.4 plus 0.04 plus 0.004, and so on. So if we write it that way, then we can see it as geometric series with the first term 0.4 and the common ratio, which is 0.04 divided by 0.4, which is actually 0.1. So as soon as we rewrite our number 0.4 repeated as an infinite geometric series like that, then we use the formula, and since the common ratio 0.1 is smaller than 1, so it satisfies this condition, therefore we can use the formula for infinite sum of the series, which is the first term, and the first term is 0.4, divided by 1 minus the common ratio, which is 0.1. Overall, we have 0.4 over 0.9. And then, by moving the dot one place value forward, we end up with 4/9. So yes, it works, the same way as we knew before. Well, let's try another example. This time the repeated sequence is just 1, 5. We have to skip the 3. So how can we see this as a series? It will be 0.3 plus 0.015 plus 0.00015 and so on. So here I would suggest that we separate the 0.3 from the rest of it, and we write 0.3, which is 3/10, and then plus a series, infinite series, where 0.015 will be the first term. So 0.015 is the first term, and the ratio between the next term and that term is the same as 0.01. So the common ratio is 0.01. You can divide this on calculator, or you can do it in your head. And this 0.01 should be raised to the n minus 1, because when n is 1, we should end up with just the first term, 0.015. And now the n will change from 1 to infinity. Okay, great. So let's calculate the sum. We have 3/10, and the sum of the series is the first term, which is 0.015, divided by 1 minus the common ratio 0.01. So that's the same as 0.99. So we have 3/10 plus, if we move the dot 3 places in the top and the bottom, we'll get 15 over 0.99, 3 places will be 99 and one more 0. So we really need to add these two fractions. You can use your calculator and even use a fraction button to add them. This overall fraction, after simplifying, it will turn out to be 52 over 165. So we know that it's a rational number. It's kind of ugly fraction, but it's possible to convert any repeated decimal to a fraction. Next, we have some application problem. Gaintown has a present population of 100,000 people, and the population is increasing by 3% each year. What will the population be in 15 years? Well, that's a question of a sequence. If A1, which is the present population, 100,000, and A2 is the increase in population after 1 year, should be 3%. So overall, the new population is 103% of the previous population. So we multiply this 100,000 by 1.03. And the next year, A3, is 100,000 times 1.03 times another 1.03 because of the next year increase. So altogether is 1.03 square. So generally, AN would be 100,000 times 1.03 to the exponent, and observe the relation between the exponent and the index of the term. It has to be 1 lower, so it's to the n minus 1. Since the question asks us about population in 15 years, and for example here the second term represents a population in 1 year, so this term corresponds to 1 year, that corresponds to second year, and so on. This is the present now. Therefore, what we really need is a not 15 but 16 to represent the population in 15 years. So A16 is 100,000 times 1.03 to the 16 minus 1 is 15. So let's use our calculator, and we round to the nearest one person. We'll get 155,797 people. So that's a predicted population in 15 years according to this model, assuming that each year the increase in population will be 3%. And now, how long will it take the population to double? When the population will be 200,000, starting from 100,000. When we follow this pattern times 1.03 to the n minus 1. So we need to find out the n. Okay, let's recall how do we solve this kind of exponential equations? Well, usually by using logarithms. So let's divide by 100,000 first, and then apply ln on both sides of the equation. So we'll end up with ln2 equals, and over here we can drop the exponent n minus 1 times ln 1.03. So n minus 1 is the same as ln2 divided by ln 1.03, which is approximately, let's use our calculators, 23.4. Therefore, the n by itself is 24.4 after adding 1 here. And what this n really represents, remember the number of years is 1 less than the index. But since n is more than 24, it goes into another year. So overall, we expect the population to double in 24 years. If this will be exactly 24, we'll write 23 here, but this is more than 24, so we need to wait another year, because after 23 years, the population will be very close to doubling, but not quite there yet. So we need to wait a bit towards the following year, so that would be the answer. The next example is really nice. I hope it will be interesting for you. Consider the figure of successfully smaller squares, like on this diagram, formed by connecting the midpoints of the sides of the previous larger square. If the area of the largest square is 1 and the process of drawing the inside squares never stops, find the total area of the shaded part of the original square. Okay, since the original square has 1 square unit in area, therefore this side is 1 and that side is 1. So let's figure out the area of the shaded triangles in this biggest square. That means just this, 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 and this all together. Well, rather than calculating area of each triangle and multiplying them by 4, it's easier to think geometrically by changing position of, for example, this triangle to fit it here, and that triangle to fit it over there. Therefore, the 4 triangles could be seen as this, 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 and that, which will form exactly half of this largest square. Therefore, its area of 4 of those triangles on the first step is equal to 1/2. And now we need to add the area of the 4 triangles in the second step. So we need to figure out what's the total area of this. Well, the total area of these 4 triangles marked in green will be half of area of that square. So it's 1/2 of area of the square, the green square. But how much is the area of this green square? Since this distance is half, and that point is also on half away, therefore I have 1/4 here and 1/4 there, which means I really have 1/2 as a side. So the area of the whole square will be 1/2 square. 1/2 square here. But what does this mean? That means 1/2 to the 3. And here I had 1/2. Let's see the next step, maybe in red. So we're talking about area of these triangles. Again, we have 4 triangles, which takes half of the area of the red square. So it's 1/2, and area of the red square, well, this red piece is half of the green piece, which is half of the original unit. So the red one is actually 1/4. Therefore, we have 1/4 square over there. But how this translates into powers of 2? Well, that's 16, so it's 2 to the 4 times 2, so it's 2 to the 5. Oh, I start seeing some pattern. It's 2 to the 1, to the 3, to the 5. So the powers are consecutive odd numbers. And the pattern will continue that way. So we really need to calculate the series like this. Infinite series, so we're calculating S infinity. Is that a geometric series? Well, let's try to divide the consecutive terms. Let's say second one divided by first one. We have 1/8 divided by 1/2. That means multiplied by 2. So that's 1/4. That will be our R. Let's see if it confirms when taking the second and third term. So 1/2 to the 5th is 1/32. Divide by 1/8 is like multiplying by 8. So yes, it's again 1/4. That seems to confirm. Therefore, our R is 1/4, and the first term is 1/2. Well, we can answer the question. According to the formula, the infinite sum is A1, which is 1/2, divided by 1 minus the common ratio 1/4. Now, if we simplify this, we get 1/2 divided by 3/4, so multiplied by 4/3, which means that the overall area is 2/3. So 2/3 of this shape is shaded and 1/3 is white. And the last application problem, a bit of introduction towards business applications. Here we'll have given formula for the future value of an ordinary annuity. Well, let's introduce the notation first. I will represent annual interest rate. N will be the number of compounding periods per year. So if we divide the interest rate per year over the number of compounding periods, we end up with the rate per one period. So this ratio is rate per one period R. And the number of compounding periods per year times time, t, in years, gives us the number of compounding periods overall in certain time. So this overall number of periods will be called M. Then the future value A of an ordinary annuity after M compounding periods is given by this big formula. We start with the P, which is the amount of each deposit. Let's say we deposit money to the bank every month for 5 years. And we assume that this deposit per month will be constantly the same. That will be our P. Then we multiply by 1 plus R, which is rate per one compounding period, to the M, to the number of periods, minus 1, and divided by the rate, R. So this time we don't need to justify this formula, just use it. And here we have application. How can we use it? Kate deposits $300 semi-annually into a saving account for her son. If the account pays 8% annually, compounded semi-annually, what is the balance in the account after 20 compounding periods? Well, let's list all the information that we have. The P, the amount of money that Kate deposits, is $300 every half a year, semi-annually. So the number of periods per year is 2. The overall number of compounding periods is 20, so M is 20. Well, we can calculate t from it. Well, we can easily figure out how long she deposits this $300. 20 periods divided by 2, that will be 10 years. So she is doing this over 10 years. And the account pays 8% annually. That means I is 0.08. That's annual interest rate. Therefore, the interest rate per one period is 0.08 divided by 2. So it's 0.04. Okay, that's actually all what we need in order to use this formula. So the amount of money in the account after 20 compounding periods, that means after 10 years, is 300 bracket 1 plus r, which is 0.04, to the m, which is 20 compounding periods, minus 1 divided by r, which is 0.04. And the rest is using your calculator. Again, please watch all the brackets. You should end up with 8,933 and 42 cents when rounded to the second place value. So this amount of money will be in her account after 10 years.